Okay, so this is the last type of convergence test that we are going to cover for series and sequences. So this is called the root test. So just like the ratio test, there are three different cases. So the first case says that our infinite series from 1 to infinity of some sequence a of n converges if the limit as n goes to infinity of the nth root of the absolute value of the sequence is less than 1. Right, so this is very similar to the ratio test, except instead of using the ratio of two things, you take the nth root, hence the name root test, of the absolute value of the sequence. So our series is going to diverge if the limit as n goes to infinity of the nth root of the absolute value of the sequence is greater than 1. And then just like the ratio test, the root test is also inconclusive if the limit is equal to 1. I'm going to try and make my arrows a little nicer because they're a little weak on this page. Right, so if you get a limit that's equal to 1, you're just going to say, okay, you know what? Root test failed, we're going to try something else, right? We have all of these different tests that we can use. You can try the nth term test, you can do geometric series test, integral test, ratio test, limit comparison, direct comparison, all of that good stuff. So if the entire rule of sequence, if that sequence inside of the series is written as a power of n, this test is probably the golden one for you. It's really hard to beat this one if you have a power of n inside of your sequence. Okay, so let's go ahead and try the ratio test with these two examples. So we can see here that we have powers of n inside of our sequence, and we can actually even rewrite this as the sum from 1 to infinity of e squared over n all to the n power, right? You could pull that exponent of n out, and I think I'm going to use that version to do my ratio test because that seems like it's going to be a little easier. Right, so the ratio test says limit as n goes to infinity of the nth root of the absolute value, and then we're just going to take that sequence, and I'm going to cheat here and copy and paste, maybe not. There we go. And put that inside of the absolute value there. So e squared over n, especially since n is going from 1 to infinity, is always going to be positive, so I don't have to worry about absolute values here. So this is really the limit as n goes to infinity of just the nth root of, I won't be lazy here and write it out. Oh, there we go. Right, so the nth root of the nth power is going to cancel out, so this is going to become the limit as n goes to infinity of e squared over n. And remember, e is a constant, so e squared is also a constant, so as n goes to infinity, this thing is going to 0, which is less than 1. And because our limit is less than 1, our overall sequence from 1 to infinity, our series rather, I'm always using the wrong word, of 2n over n to the n power, converges by the root test. Okay. Right, and so again, we have this power of n here, so that's a really good indicator that we should use the root test. So I'm going to take the nth root of the absolute value of our sequence, and again, since we have 3n plus 4 over 2n is always going to be positive, and then the n power is always going to be positive, so we don't really have to worry about the absolute values. The absolute values are just there in case you have an alternator, so you can kind of cancel that out. You don't have to worry about it. So the nth root is going to cancel out. I'll be really thorough here though and say, you know what, we don't need those absolute values, so we're just going to have this guy on the inside. right? And then the nth root and the nth power are going to cancel out. And then we have matching degrees in the numerator and denominator, so we're going to get the ratio of the coefficients is going to be our limit, but that is greater than 1, which means that we are going to diverge. So therefore, our series of 3n plus 4 all over 2n raised to the power of n diverges